So we spent a lot of time talking about the equilibrium condition and what goes into framing it. We haven't really spent as much time, though, actually calculating these equilibrium states, but that's going to change in this video. Our learning goals are to use the equilibrium constant and initial concentrations to find the resulting equilibrium state for a reaction. So let's go back and consider reaction species concentrations as they evolve in time during the course of a reaction. So with any given reaction, and I'm going to use the one that's specified up here in the very top, it's just the abstract A plus B goes to C plus D, we're going to assume that these each have initial concentrations that we know. In some cases, if in a particular problem you may be given that they're zero, but you will know what they are generally. And they're going to change during the reaction. Now, what I want to do in order to specify this change, and I'm going to use the variable x to indicate an incremental change in concentrations. I'm going to use a minus sign if it's being used up. I'm going to use a plus sign if it's a product that's being produced by the reaction. So if I look at species A, which is the first reactant on the left-hand side, I'm reacting A, so its incremental change is going to be negative x, but I'm going to multiply that by its balanced equation coefficient, little a. Now, there's a reason for doing that because I know that these reaction species have to combine in the right ratios, in the mole ratios that are given by the balanced chemical equation. So if I define A reacting this way, then I can define B reacting by minus B times little b times x. So now you can see I can use the same x for both of them, and I've put in the right proportions from the balanced chemical equation by using those coefficients. Now, what happens now when I'm talking about C? C is a product, so it's being produced by the reaction. So instead of a minus sign, I'm going to have a plus sign. So the amount of C that's being produced is going to be plus little c times x. And the amount of D that's being produced is little d times x. Now, if I were to chart the concentrations later, I started at A0, the thing at the top of the slide, and I lost AX, so my concentration at a later time is going to be A0 minus little a times x. Similarly for B, I'm going to have B is B0 minus little bx, and so forth and so on. Notice that in C and D, it's not a minus sign but a plus sign. They're increasing as time goes by. So by setting up our concentrations this way, I've made it so that x is now the only variable I need to solve for in order to specify the equilibrium state. Now, we can organize our process to do this, and this is what I want to talk about now. It's a technique called ICE tables, and instead of using the most general A plus B goes to C plus D reaction, I'm going to use the one that's written up here where I just have A plus B goes to 2C plus D. So I only have one coefficient in the balanced equation that's different from 1, and I'm using that mostly to illustrate where it comes in. So we can organize all of this by creating a table, and this is what the table looks like. All right, we list the reaction species across the top, and there's going to be one column for each of the reaction species. On the far left, I've gotten three letters, ICE, and that's where the term ICE table comes from, but it's not talking about solid water. It's talking about a different kind of ice. It's an acronym, and it stands for the following. The I stands for initial. This is where I'm going to put the initial concentrations of all the species in the reaction. The C is for the change. So that's where I'm going to put the incremental change that's going to happen while the reaction is happening. And finally, the E stands for equilibrium. That is the concentration that each of these species is going to reach when it reaches equilibrium. And that's, in effect, where they will stop evolving. That's going to be the end point for this reaction. So now if I fill in this table, I know what the initial conditions are going to be. They're just going to be the initial concentrations of A, B, C, and D. Usually I will be given that in a problem. Now what about the change? Okay, just as I did in the previous slide, I'm going to use x as my increment for change. I'm going to use a minus sign to indicate the things that are disappearing and a plus sign for the things that are appearing. And I'm going to use the coefficients in the balanced chemical equation to multiply x. So the increment of change for A is going to be minus x. The increment of change for B is going to be minus x also, because it has the same coefficient of 1 in the balanced equation. Now for C, it's got to be plus 2x. We're producing C in this reaction, it has a coefficient of 2 in the balanced equation, so it'll be plus 2x, and for d it'll be plus x. Now, what I'm going to presume is that I'm going to let this reaction run until it reaches equilibrium. And what I want to do is solve for the value of x that satisfies the equilibrium condition. So that means at equilibrium, it will have A will have started at A0, it will have changed by an amount minus x, so at equilibrium, its value will be A0 minus x. Now I'm going to jump over to C and show that when C reaches equilibrium, it will be C0 plus 2x. Now look what's happening. I'm just adding the first two rows together. So for B it should be B0 minus x, and for D it should be D0 plus x, and indeed it is. So when I fill in this ICE table, all I need to do is stick the initial conditions that are given to me in the problem. The one piece of work that I have to do is I have to figure out what the increment of change is, but that's pretty easy. All I'm going to do is make it a negative sign if it's something that's disappearing, like reactants in this case, a positive sign if it's something that's being produced, and then I multiply that increment of change by the balanced equation coefficient. I simply add those first two rows together to get the last row, and then what do I do with it? Well, then I'm going to use those expressions for each concentration in the expression for the equilibrium constant. So I've drawn here the equilibrium constant as the concentration of C squared times the concentration of D, and those are divided by the concentrations of A and of B. Now when I substitute in all of the entries that are in the E row of this ICE table, I get a really messy expression, right? I won't even read it out loud, but it's a messy algebraic expression. Well, guess what? That is the equation that you need to solve in order to find the equilibrium expression. But what I will be advising you to do is to use Wolfram alpha or some other technique where you can just plug these equations in and it will do the hard work and solve it for you. I'm not interested in teaching you math. I am interested in you setting up the math correctly. So let's look at a specific example. That particular thing, by trying to keep to a general case, made it look much harder than it actually is. So here is an equilibrium that involves hydrogen fluoride, and it's actually an acid dissociation reaction where H leaves the hydrogen fluoride and attaches itself to water to make the hydronium ion H3O+, and leaves the fluoride ion F-. This has an equilibrium constant of 7.2 times 10 to the minus 4. And just for the sake of this example, I'm going to say that the initial concentration of the hydrogen fluoride was 0.62, but the initial concentrations of the hydronium ion and the fluoride ion were both 0 to begin with. So now I need to set up my ICE table, and you'll see that I've headed each of the columns with the particular concentration that I'm going to list in that column. And for HF, I know the initial concentration is 0.62, but I know the initial concentration of H3O+ is 0, and the initial concentration of F- is 0, so this is going to be relatively easy. Now all of the coefficients in my balanced chemical equation are 1, so I'm going to have a minus x for the increment of change in HF, plus x for H3O+, and a plus x for fluoride. When I add these two rows together, I'll get these results down below. Now you can see this is a much simpler expression than the ones I had on the previous slide. So when I write the expression for the equilibrium constant here and then convert it using those concentrations listed in the E row of the ICE table, it's not so bad. It's x times x divided by 0.62 minus x. This again is something you can easily plug into Wolfram alpha or some other, or you can solve the quadratic formula if you wish. Whichever way you do it, you will find that x is equal to 0.0208, and that is also equivalent to the fluoride ion. It's also equivalent to the hydronium ion. If I want to get the equilibrium concentration of HF, I will need to subtract this value from 0.62. All right, so what we've introduced here is a problem-solving method, and I want to specify exactly what you need to retain from this lesson so that you can be successful. First, you need to know how to assign the initial concentrations in the ICE table. And that should be pretty easy, but it means you have to read the problem and get those values from the problem if they're given. If they're not given, usually you can assume that they're 0. You need to be able to set the appropriate increment of change. Now, I've tried to give you enough clues to do that. It's not that difficult to do, but you do need to do it correctly or you won't get the right answer. You need to develop expressions for the equilibrium concentrations, that is the E row of the ICE table, and then you need to be able to write down the correct equation to solve for X. If you can do all of that and you can plug this into Wolfram Alpha or some other mathematical solving software, you should be able to solve any equilibrium problem that anyone can give you.